Good morning, good afternoon, good evening, mammals. We're going to be doing our last trend today for NTI number 5, which is for Tuesday, March the 17th. So, our last trend is electron affinity. It's on the back side of that same paper that I left you with on Friday. Again, if you've lost that paper, I'll have it posted as a PDF in Google Classroom, so you can check that out. Electron affinity is very related to electronegativity, so we're going to talk about that, do the same thing where we look at what happens to the numbers as we go across, what happens to the numbers as we go down, talk about the definition, and then you guys are going to paraphrase some questions for me at the end, and that's what you're going to be actually submitting. So, get straight to it, keep this video brief. If I look at these values, these fluctuate a lot. This is probably the least consistent trend, so that has the most exceptions, so that's why I've saved it for last. There's a lot of exceptions. This fluctuates a lot, but in general, the elements over here in this column are higher than the elements over here in this column, so we're going to say cautiously that it increases. And the next question is, can you find some exceptions? Well, there's a boatload of exceptions. There's some little variations here and here, but we've got that same variation here where we've got them at the end of the D block switching into the P block. Again, especially with this trend, I don't want you to worry about these exceptions other than what's up with the noble gases, which we'll come to in a second. Just know that this trend increases as you go to the right, with the exception of the noble gases. Okay, as we go down, again, a lot more kind of exceptions here, but in general, as we go down, this trend decreases. So I'm just going to sort of focus on this column here because it's pretty consistent, or this column over here because it's pretty consistent. So we're going to say as we go down, this, whoops, I don't know what other button I pressed there. I want to make that go away. Decrease. And again, lots of exceptions that aren't going to be important to you. Okay. Let's look at what this trend is actually measuring. So number 7, electron affinity is the energy released when an atom gains an electron, becoming an anion. So this is sort of like the flip of ionization energy. Ionization energy is the energy to remove an electron. I like to think about it as the energy that it takes to buy an electron from that atom. This is the energy that the atom releases when they gain an electron. So I like to think about this as the amount of energy that these atoms are willing to pay for it. So if I kind of go with that analogy, which atom and which part of the periodic table is like most jonesing for an electron? Like fluorine's over here twitching and scratching itself because it is so like desperate, hard up for an electron, and it's like, I will pay you lots of energy for an electron because it's so close to becoming a noble gas. Whereas atoms over here, they really don't want extra electrons. Their best path to a noble gas is to lose. So they have very low electron affinities. And that kind of also explains why the noble gases have negative electron affinities. The noble gases, they don't want to gain or lose an electron. So we'll come back to them here in a second. So the two questions that you need to paraphrase is, the noble gases are furthest to the right, but they have the lowest electron affinity. So I'm going to give a similar explanation to these that I did for electronegativity. As we go to the right, effective nuclear charge increases. So helium is our highest ENC, but this corner has our highest electron affinity. And the explanation that I gave for that with electronegativity is going to be the same thing that I talk about here. If I draw a noble gas like neon with 10 protons and 10 neutrons, and I put its electrons there, 1s2, 2s2, 2p, 6. It has a high effective nuclear charge because its valence electrons see 10 positive protons, but only 2 inners. However, if we give it an electron, it has no place to go on this second shell. So it would have to go into the 3s. And now our added electron would see 10 protons, but now 10 inner electrons, because it now has all 10 of these electrons as inners. So this means that we have basically equal amounts of attraction and repulsion. So it's going to be very, very difficult for neon to accept an additional electron, even though it's very attracted to its own. So the noble gases have very low electron affinities because if you try and give them an electron, it is going into a new, fix that, it's going into a new shell further out, which is going to have a lower effective nuclear charge. So that can help you paraphrase: the noble gases are furthest to the right, but they have the lowest electron affinities. Why do you think this is the case? So that discussion needs to have something about, even though they have high effective nuclear charges, when you give them an electron, there's no room in that shell. There's no room in the end. It's got to go out in the stable of the next shell outside, which is going to be further from the nucleus and weakly attracted to it. Lastly, I added this one in. This wasn't on there, but I'll put it on the Google Docs. What does a negative electron affinity mean? Well, if this is the energy that is released when you give it an electron, a negative release would mean it actually has to absorb energy. So a negative release is saying that it must absorb energy. You have to pay these atoms energy to accept an electron. So energy must be given to the atom to absorb electron, or to gain an electron. So it has to absorb that energy. So that's this last trend. It's the one that's most filled with exceptions. The only exception that you need to know about, just like with electronegativity, is why, even though it's increasing as we go to the right, the noble gases are like the lowest one in each row. And so we're going to have some practice problems coming up where you're asked to rank them, and you have to be careful when you're doing electronegativity or electron affinity. And I've got a noble gas. So that's the main takeaway that I want you to get away from this, is these noble gases are the lowest amount. It's almost as if you could think of them as being over here. So I'll kind of prime you for that when you do some practice problems in coming NTI days. But that's going to wrap it up for today. I'll have a Google Docs where you can post your answers to questions 8 and 9 and turn that in to me to verify that you watched this video. So, as always, take care of yourself and others, practice good hygiene, and I'll see you on the flip side.